welcome back. In this session, we are going to see about uninformed search algorithms that are DFS and BFS. We are going to see how these DFS and BFS are used to reach our goal node. That is, in such problems, we have to search for the goal nodes. We will be having some graph problem. So in that graph problem, we will be having starting node and also we will be having the goal node, and we don't have any other information about goal node, that is how to reach to the goal node and also which path I have to take to reach the goal node. This information was not given to me. So that's why these DFS and BFS is known as uninformed search. So in this DFS is a depth first search. In this depth first search, we are going to use stack data structure. In this depth first search, we are going to use stack data structure as open. That is, whatever in our previous algorithms we have seen open as a bad data structure. But in this DFS algorithm, we are going to assume that open is acting as a stack data structure. So what is the basic principle of stack is last in first out. That is, the element which is inserted at the last will be the first element which will be deleted first. So while solving for the search problem, so we will start from the starting node and we will search for the goal node with the immediate neighbors. So in this immediate neighbors only processing. So this is the processing of the DFS. Here we can see the algorithm of DFS. So in this algorithm, the first step is, so initialize stack so that it will be having the only root node. That is, this stack is nothing but it is a open. So this open data structure will be acting like a stack. In that stack, we are going to make sure that the initialization condition, that is only the starting node or root node, will be given as the input. So it is nothing but a starting node. The starting node will be given as an input, and after that we will check for the condition, that is either goal node is achieved or stack is not empty. So until these two conditions have to be, so any of the two conditions have to be false, we will try to execute all the statements. So these statements will be, so these four statements will be executed until these conditions are achieved. That means these conditions are, until these conditions are reached. So first, initially, so the stack is having, so starting node. So from that starting node, I will try to explore all the reachable states from that starting node. For example, if I am taking a graph, in this graph, for example, this is the example graph. In this graph, we have to check whether, so we have to take this particular graph as a problem. In this uninformed search algorithms, DFS is the first algorithm. In this DFS algorithm, it will be using a stack data structure. That is, in our earlier algorithms, we have seen that the open is a bag-like data structure in which each and every element will be having the same probability to get picked. So in this particular algorithm, we are going to use stack in place of open. That is, open is acting like a stack. So what is the basic principle of stack is last in first out. So LIFO. So in this last in first out, that is, so the element which has entered into the data structure last will be the first element deleted from that particular data structure. So here we are going to use a stack. So the algorithm will be like this. So in this algorithm, so the first statement is the initialization condition. So in which the stack data structure will be having the root node. Root node is nothing but a starting node. So it is a starting node. Next we will check for the while condition. So in this while condition, so we are going to check two different conditions that are either goal node has goal node reached, this is the first condition, and is the stack is empty. So these are the two conditions. Until these two statements, until these two conditions are achieved, that is either I have to until these two conditions that are either the goal node have to be reached or the stack have to become empty. Until these two conditions are achieved, we are going to execute so these four statements. So these four statements will be consisting of, so first I will, so the stack, whatever the nodes that are present in the stack, I will try to delete the element from the stack, that is pop operation. I will apply pop operation on the stack and I will delete one particular node from the stack. So that node will be stored in node n, and I will check whether this particular node, if this node n is a goal node. If that particular node n is a goal node, then I will return success and I will calculate the path. So after generating the path, I will calculate the path and I will show this particular path to the, so wherever the DFS was applied. Next, if the particular node is not a goal node, that means this condition is true, then this statement is executed. If this statement, that is if n is goal node is not true, then I will execute this else statement. So in this else statement, so I will push all the successors of that particular node n. So all the successors of node n onto stack. That is how I am going to push all the successors. Means first I will apply move-gen function on this particular node n. So by using move-gen function, I will get all the successors of node n. So all the successors which are generated by move-gen function, in that if any nodes already present in the closed data structure will be deleted and the remaining nodes will be pushed onto stack. So after that, again while condition will be checked whether goal node is reached or stack is not empty. So again, if it is not true, means next I will again pick some other node and I will store that node in the node n from the stack. So after that, again I will check whether n is a goal node. So this process will continue until either goal node have to be reached or the stack have to be empty. So this is the algorithm for the depth first search, and using this algorithm we are going to search for the goal node in a search problems. For example, this is the tiny search problem. So this is the graph we have been given. So in this graph, S is the starting node and G is the goal node. First, the initialization condition, that is, so first the stack have to be empty and it will be having the starting node, that is S. So then I will, so this is node search tree will be like this. First S. So I will in the algorithm, first I am going to delete. So check whether goal node is reached. Until now goal node is not reached, and also I will check whether stack is empty. This stack is not empty. So I will pop an operation. I will apply pop operation. By applying pop operation, this S will be deleted. This S will be deleted from the stack and it will be stored in node n. So this node n will be having. So after this S is deleted from the stack, it will be stored in node n. So this node n, I will check whether S is a goal node. S is not a goal node. So I will apply move-gen function on this particular S. So move-gen function will be applied on this particular S. And what are the successors of S is, so A, B and C. So the output of move-gen function on S will be A, B and C. So for this one, I will have three successors. So A, B and C. Now S will be moved to closed state, and open will be having open means stack will be having A, B, and C. So I have to enter A, B, C. So I can enter A, B, C into stack in any order. So I am entering like this: C, B, and A will be entered. Now the stack is having A, B, and C. So now again I am going to check while condition. While condition is whether goal node is reached. Goal node is not reached. So next condition is whether stack is empty. Stack is also not empty. So I will apply pop operation. By applying pop operation, this A will be deleted from the stack and it will be stored in node N. So after that I will check whether A is a goal node. So A is not a goal node. So I will apply moveGen function on A. So after applying moveGen function on A, so the successors of A are S, B, and E. So in this one, already S is in closed. Already S is in closed, and also B is in already in the open. So S and B are ignored, and E will be added as a successor of the A. So successors of A is E. So this E will be pushed into the stack. So next again while condition will be checked whether goal node is reached. Goal node is not reached, and also we will check whether stack is empty. Stack is not empty because stack is having three elements, that are E, B, and C. Three elements are there, so stack is also not empty. So I will execute the while condition. In that while condition, the first statement is I have to apply pop operation. So after applying pop operation on this stack, so this E will be deleted and it will be stored in node N. So this node N will be having E now. So next statement is I have to check whether E is a goal node. So I will check whether E is a goal node. Clearly E is not a goal node. Else part will be executed. In that else part I have to apply moveGen function on E. So I will apply moveGen function on E, and the successors of E are so D, G, and A. So among this A, D, and G, so we can see A is in the closed. So A is in the closed. So A and S both are in the closed. So the successors of E means A, D, G. So in this one, A is already in the closed, and D and G will be added. So D and G will be added. So this D and G will be added. So this will be added to the stack. D and G have to be added to the stack. So I am adding like this. First G will be inserted. After that D will be inserted. Next I am going to check whether goal is reached. Goal is not reached. And also I will check whether stack is empty. So clearly stack is not empty. So I will execute while condition. So in that while condition, first statement is I have to apply pop operation on stack. By applying pop operation on stack, so this D will be deleted from the stack and it will be stored in node N. So after deleting node N, I will check whether D is a goal node or not. So D is not a goal node. So D is not a goal node. So D is not a goal node. So else condition will be checked. So I have to apply moveGen function on D. So by applying moveGen function on D, so the successors of D are B, C, E, and G. So these four are the successors of D. So in this D, C, E, G, so E is already in the closed, so it will ignore, and also B is already in open, and also C is also already in open, and G is also already in open. So all the successors of the D are already either in open or in closed. So the successors of D are not newly generated nodes. So I will not again add any of the successors to the open. So that is stack. So again I will check the while condition whether goal condition is reached. Goal condition is not reached. Next I will check whether stack is empty. Stack is not empty. Now I will execute the while condition. In that while condition, while loop, so the first statement is I have to apply pop operation on stack. So I am applying pop operation on stack means this G will be deleted and this will be stored in node N. So I will check whether this node N is goal node or not. So node N means node G will be evaluated. So by applying goal test condition on G, so it will come to true. That means this is a goal node. So whenever this goal node, that condition, goal test condition will be true, then we will return success, and also we have to generate the path. So the path will be generated like this. So first, so G will be calculated. Next its parent, that is E. Next its parent A and S. So it will be reversed. So yes. So it will be reversed and the path is S to A and A to E and E to G. So this is the path from S to G. So this is the example for the depth first search. So when it is applied on any such problems. Next algorithm is the BFS. BFS is the breadth first search. In this breadth first search, in DFS we are used stack as an open. That is stack data structure is used as open. So in this breadth first search we are going to use queue data structure as open. So this queue data structure will follow first in first out. So that is the element which has entered into the queue first will be the first element which is deleted. So this algorithm is like this. So it is same as DFS. The only difference is instead of stack we are using queue. So first the initialization statement. So that is I am going to initialize a queue which is having only root node. Root node is nothing but a starting node. So with that starting node in the queue node, I will check the while condition. While condition is I have to check whether goal node is reached. So goal node is not reached, then also queue is not empty. Until queue is not empty, I have to execute. So these 4 statements. So in this statements, the first statement is I have to delete an element from the queue. So deq first node from the queue. So if I am applying the deq, then the element that is pointed by the first, that is front is will be deleted. So this queue, this first statement will return some node to node n. So after that, the node n will be having some node. So that node will be, I will check whether n is a goal node. So I will apply test condition on n. So whether it is a goal node or not. So after that one, this goal node is. So based on this condition, so whether if it is a goal node, then I am going to execute this return. I will return successes, and also I will generate the path and I will return the path. Or if this particular n is goal node is not true, so that is false, then I will add all the successors of the particular node n, all the successors of node n onto queue. So that is I will apply moveGen function on this node n, and I will nq means I will add all the successor nodes into queue. So this is the algorithm for the BFS. Using this BFS algorithm also we will try to search for the goal node in the search problems. So we will see one example. So that is tiny search problem. How this BFS is used to solve that tiny search problem. So this is the tiny search problem. So in this In this graph, S will be the starting node and G will be the goal node. So by using breadth first search, we have to search for the goal node. So for applying BFS, we need to have a queue data structure. So this queue data structure will be like this. So from this end, I will delete an elements. From this end, I will insert the elements. So initially, so the elements will be. So initially, this queue will be having S. So first, this is the initial condition. This queue will be having S, and next I will check for the while conditions. So in this while, there are two different conditions. First condition is whether goal node is reached. So until now goal node is not reached, so it will be so true. Next condition is whether queue is empty. So this queue is not empty, so I will execute while statements. So in this while statement, the first statement is I have to delete an element from the queue. So and I have to store it in the node n. So this node n. So I will delete S from queue and I will add it into node S. So this node n will be having, so starting node, that is S. So and I have to, the second statement is I have to apply test condition on this node n. So I am applying test condition with this SC will be applied to the test condition. So goal test of S will be false because S is not a goal node. So I will execute else part. In the else part, I have to apply Mosian function on this S, and I will add all the successors of S into the queue. So I am applying Mosian function on S means, so what are the reachable states from S are A, B, and C. So these three states that are A, B, C nodes will be added onto the queue. So this the output of Mosian function on S will be A, B, and C. So in our search tree, we are having in the closed data structure only we are having S. So I am not going to these ABC are the newly generated nodes. So I will add this ABC into the queue. So this ABC will be added into the queue such that first I will add A, next I will add B, next I will add C. So next again I will check the while condition. In this while condition, first condition is whether goal node is reached. So goal node is not reached, and the second condition is whether queue is empty. Queue is also not empty. So I will execute the while condition. So while in the while loops, the first statement is I have to delete an element from the queue. So from this end, if I delete, A will be deleted, and this A will be stored in node N. So after that, I will apply goal test condition on A. So if I am applying goal test condition on A, it will be false because A is not a goal node, and I have to execute the else conditions. In that else condition, I have to apply Mosian function on A. After applying Mosian function on A, the reachable states from A are S, B, and E. So in this one, S is already in the closed and B is already in the open. So I am going to add the newly generated node, that is E, onto Q. So E will be added to the Q. Next again while condition will be checked. In while I am having two conditions. First condition is whether goal is reached. Here goal is not reached, and also the second condition is Q is not empty. So both are true. So I am going to execute the statements that are present in the while loop. The first statement is I have to delete an element from the queue. So after deleting, I am applying DQ operation, that is deletion operation. After applying DQ operation, B will be deleted. B will be deleted and it will be stored in node N. And this and I will apply goal test condition on node B. So I am applying node test condition means it will be false because B is not a goal node, and I have to execute the else statements. In this else statement, I have to apply Mosian function on B. So after applying Mosian function on B, so the successor states of B are the reachable states of B are S, A, and D. So in this one, the successor states of B are S, A, and D. So for this, S was already in the closed data structure, and A was already in the closed data structure. So and B. So D is the newly generated node. So I'm going to add. So I'm going to add D as a child of B. So this D will be added to Q. Next, again I am going to check. Next, I am going to check the while conditions. So first condition is whether goal node is reached. Goal node is not reached. Next, I am going to check whether Q is empty. Q is also not empty. So I am going to apply deletion operation on the Q. After applying deletion operation on Q, C will be deleted and this C will be stored in node N. So the next I am going to apply goal test condition on C. It will be false. I have to apply move gen function on C. So what are the reachable states from C is S, D, and G. So in this one already S is in closed and D is already in open and G is the newly generated node. So I am going to add G to the Q and also to the search space. So C will be moved to closed data structure. Now this again I am going to check the while conditions. Goal is not reached and also I am going to check whether Q is empty. Q is not empty. So this process will be continued. So now E will be deleted and this E will be stored in node N. So goal test condition is applied on E and this E is not a goal node, so it will be false and I have to apply move gen function on E. So after applying move gen function on E, so A, D, and G will be the output of the move gen function on E. So A and D already, A is already in the closed and D is already in the open and G is also in the open. So there are no newly generated nodes from this E. So I'm not going to add any nodes of E, successors of E. Next, again while conditions will be checked. So and after the conditions were checked, so D will be deleted and this D will be stored in node N. Again D will be checked for the goal test condition. It will be false and have to apply move gen function on D. And the reachable states from the D are B, C, E, G. So in this B, C, E, G, so B is already in closed and also E is already in the closed, C is already in the closed, G is already added to the open. So I am not going to add any successors of D because they are not newly generated successors. So again I am going to check the while condition. So goal node not reached and also Q is not empty. So I am going to delete a node from the Q. So G will be deleted and this G will be stored in node L. So after that I am going to check for the goal test condition. So this goal test condition on G will be true as G is a goal node. So after I am getting true, that goal test condition as true, I am going to return success and I will generate the path. So the path will be first G from so this G was happened from C. This G was added to the search space by using C. This C is added from the search space by using S. So after I will generated the path, I have to generate the path from S to C and C to G. So this is the path I am going to get by using BFS. So this after applying this BFS onto the tiny search problem, So the generated path is S to G, S to C and C to G. So by using DFS, the path is S to A and A to E and E to G. So these are the paths generated by DFS and BFS. Now we are going to compare the performance evaluation of these DFS and BFS. After comparing the DFS and BFS, we can see which algorithm performs better. So here we can see the behavior of DFS. So this particular node will be the starting node and this one is the goal node. So by using this stack, this is an infinite search space. To understand the behavior of DFS, assume we are having an infinite search space. So this is an infinite search space in this one. So this is the starting node and this is the goal node. So I have to go from such a starting node to the goal node by using DFS. So this DFS we can assume. So this in this algorithm of DFS we are going to use stack data structure, that is, so the immediate neighbors will be checked. So for suppose I am starting node will be having some childs. So in this child I have selected only some X child. So the next searching will be done with the successors or the neighbors of that particular X node. So here, so this is the starting node. I have applied Mugen function on this S. The reachable states from S are these 6 nodes. So in these 6 nodes, so I have selected this particular node. So next, based on the property of DFS, the successors or the reachable states from this particular state will be examined first, other than these 5. So because of this, the searching will be carried out like this. So or it may be deviated and it will go to the, as it is a infinite search space. So our goal node may be presented at one particular direction, and based on my particular DFS, so this direction will be deviated. So because by using DFS, if I am going to the right path, then only I am going to go to the goal node. So at any time I can deviate from that particular path and I will go into some other path. So in that path there is no chance of going to the goal node. So by using this DFS, so this algorithm is not complete. That is, so in some situations I cannot go to the goal node in the infinite search space. Whereas in finite search space, it is finite search space, this DFS is complete, but in infinite search space it is not complete. So this is the behavior of the BFS. In this BFS, for all the childs of the first starting node will be checked. So after checking them, so the next, after checking, so I will check for the childs of these children. So like that, this particular procedure will be continued until I have found goal node. So this process will be continued. This process will be continued and my goal node may be reached. So while coming, this particular BFS is complete because I can go to the goal node, but the time taken to reach the goal node will be exponential. That is, it will be very high. So now we can see the time taken under the best cases for the DFS and BFS. So for example, so this is the search tree of the both DFS for that particular problem. So from this nodes, like that we will be having. If this is the search tree, so DFS will be perform better if the particular goal node is presented here. So by applying DFS on this particular search problem, so this if I am having goal node in this area, then DFS will perform better because so BFS will be checking level by level, it will be checking, so until it will be reaching this last this level, it will take more time. But by using DFS, it will go like this. So DFS will be better in achieving this particular task because goal node has presented here. So by using if the goal node is presented here, so BFS will be the first. By using BFS, I will reach to the goal node easily or quickly. So while DFS will be sweeping from left to right, so this particular node will be the first. If the goal node is presented in this particular place, then BFS will be the best algorithm to apply. So if the goal node in this particular search problem, if the goal node is presented here, so then if you use DFS or BFS, it will take same time, that is it will take all the search total search tree have to be examined to get to this particular node. So in running time, so for to the best time for the BFS is to have the node here. For the best case for the BFS is to have the node here. So for the worst time for both the algorithms, the goal node will be presented in this area. So this is the search frontier from both DFS and BFS. So from this one, I am going to calculate the space complexity. So this space complexity, so these blue nodes presented in this particular one are already in the closed node, that is they have been examined and get to a conclusion that the particular node is not a goal node, and so I will search for that particular inner neighbors of that particular node. So if I am using DFS, so this DFS we can see, so these pink nodes are the nodes that are presented in the open. So by using BFS, so in this situation, so for reaching this particular level, we can see, so these are the nodes that have been processed and these are the nodes that are in the open. Clearly we can see by using BFS, we are storing more number of nodes in the open than the stack, that is DFS. So using DFS in open, we are going to store this number of elements, and also by using BFS. So the space complexity of BFS is worst than the DFS. So these are the performance evaluators. So first one, time complexity. So we have seen that in the worst case, both are having the order of B power D. Here B is the branch factor, so D is the depth. So both are having order of B power D. So both are having exponential time complexity. And also by using the space complexity, we can see BFS will be having order of B power D, whereas so DFS is having the space complexity of order of B into D. So compared to this BFS, so DFS is better. So it will be having linear space complexity. So next, coming to completeness. So this BFS will guaranteedly find the goal node because it will go on circling through its successors until it will reach the goal node. So here by using BFS, we can guarantee that the whatever the goal node, if any goal node is present in the such a space, then this BFS will guaranteely find it. If it is finite data, if it is a finite such a space or infinite such a space. So by using it, as it is going to have a goal node, then it will be having a path. So whatever the path that we got by using BFS will be the shortest path. So coming to DFS, so this DFS, it will not for the infinite such a space, it is not complete, because it may deviate from the so particular path. So here by using DFS, it is not a complete, and also as goal node is not reached, so the quality of solution, there is no guarantee, because their path may exist or not exist, and also whatever the paths we are getting from the DFS, they are not the best paths. Maybe they can the best path can come, but always the whatever the path that was written by DFS, it is not a shortest path. The path that is written by BFS will always be a shortest path. So these are the comparison between DFS and BFS. So in this comparison, we can see so DFS is better in handling space. So whereas by using BFS, we are going to get the shortest path. So in the coming algorithms, we have to make sure that the whatever the in the search space, we have to maintain space complexity better like DFS, and also we should get the shortest path like BFS. And also we have to make sure it should be complete, and so that it can get the path. So in the coming algorithms, that is depth bound DFS and the depth first iterative deepening. So these are the uninformed searches, so which are aimed to have a better space complexity and also try to get best solution path. So we are going to modify DFS into DBDFS, that is depth bound DFS, and also depth first iterative deepening. So these two algorithms will be focusing on how to improve DFS, so that it will be having the so that this particular DFS algorithm should be complete. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.